Welcome to the presentation on the Desmori Motorcycle Riding Simulator for Human Factors Research, hosted by the Wuerzburg Institute for Traffic Sciences. Join us as we investigate the research activities led by Raphael Pleß, motorcycle safety researcher and simulator developer, and Sebastian Will, human factors specialist. This riding simulator, developed by WIVW, offers insights into motorcycle rider behavior, focusing on aspects like distraction and emergency braking.
So, buongiorno, good morning everybody. We are very honored and happy to start this first day dedicated to motorcycle simulation here. So, before we get started, one important question is, who of you is an active motorcycle rider himself or herself? Maybe you can just raise hands. I would say a quite good share. Okay, and who is, okay, you're riding twice. That's very good. And who is an active motorcycle simulator rider? One? Perfect. So you are our expert, Christian, and we hope that after this presentation, you're very keen on becoming one. So we share our, let's say, experience we gathered throughout the last decade, developing our motorcycle riding simulator that we use for human-in-the-loop testing. A quick word on the company, the Wuerzburg Institute for Traffic Sciences that Raphael and I are working for is mainly providing human factors research and development services. So whatever topic is addressed, our focus is always on the human being, on the driver, on the rider, and we do this mainly in the mobility domain. And the second kind of column of our company is the development of our driving simulation software C-Lab that is tailored to fit the needs in human factors research. So for instance, we had the requirement that the virtual map is not geographically consistent, but that the map itself develops based on the driver or rider behavior. And this wasn't really available 25 years ago, and that is why we started that. So that's the company. And from 2010 onwards, we had more and more requests from companies from the motorcycle domain, from OEMs or Tier 1 suppliers, on research questions where we thought it's appropriate to have a powerful research tool, a simulator, such as we have those in the automotive domain being established already. And as there was no motorcycle simulator available that you can buy from stock, we kind of decided to design and construct our own simulator, and we will take you a little bit through that decade with different steps in the development of the driving simulators that we are running in our company. And here we'll hand over for the first time.
Hi everybody. So I want to give you a quick insight in why it is so difficult to build a motorcycle simulator and why it is so different than riding a real motorcycle. So I will walk you through this slide a little bit. We see here like the standard system consisting of the rider, the motorcycle, the environment. Obviously there are a lot of signals going on. The rider can control via the steering, via the leaning, via the longitudinal controls, everything that is happening with the motorcycle. Obviously, the motorcycle dynamics can become very complex. We have all those gyroscopic effects, etc., etc. Most of you probably know about that. And then the motorcycle generates some outputs that we as a human perceive. And these outputs are overlaid with some environmental influences. And all of that is in the end perceived by the rider through visual, auditory, haptic, vestibular, and thermal cues. And now the good thing is that the rider, how he behaves and how he decides what to do, all of this, everyone knows how to do that, right? Because we already do this since we are like 3 years old, 2 years old. So from the beginning, when we start learning riding a bicycle, we really get a deep understanding of what we are doing on the motorcycle, on the bicycle, etc. The dynamics are the same. But unfortunately, knowing is not really what we need in the motorcycle while riding. I can ask many, many motorcyclists what they are doing. They can try to explain something, but most certainly they are wrong in terms of counter-steering, positive steering, etc. Like, it's not a deep knowledge that they have about riding, but it's something, unconscious, I would say. And that is also then a big issue with the motorcycle simulator. So if we consider that in this system with all these signal flows, all these perceptions, we exchange the motorcycle and the environment with virtual components, like the mock-up and the platform that is moving in a certain direction, and with the laboratory providing visual cues, etc. Obviously, there will be some false cues, there will be some resolution issues, etc., etc. And all these topics will come down to the rider behaving differently. And now, especially in some basic, typical riding actions like balancing, what you have to do at the first instance when you get on the motorcycle, when you're starting the motorcycle, the first thing you have to do is balancing until the motorcycle develops its own self-stability. And this is a very skill-based mode where the rider doesn't really think and understand what should I do to balance the bike, but he just does it. And this has an effect on steering, on leaning, on the longitudinal controls, which are then fed back to the mock-up, to the platform and everything. So if we don't succeed in having a certain quality, this mode of balancing is rather hard to do on a simulator. Okay, for the further course of this presentation, we will show you a little bit more details about requirements and challenges that we have seen throughout the development in the past decade and how we dealt with them. Just to give you a quick oversight about some of the more complex topics. We're starting with the dual loop rider control. So at the beginning, when we started to develop our dynamic riding simulator, we said, okay, the riders must be able to steer the vehicle by a combination of handlebar input and body motion input. We know that this is true also in real life. We are not only controlling the motorcycle by the handlebar, but our body weight has an effect on the vehicle dynamics. We call that the bidirectional steer-roll coupling. So as soon as the motorcycle is being steered, it will have a roll reaction, vice versa. And both of these steering and leaning inputs and feedbacks, we can feel them as a human. We wanted to show both of them in the simulator. Our solution to that was developing a rider-induced roll torque mechanism. So you can see here that our mock-up is put on a roll axis, a mechanical axis where it can rotate about, but this rotation is stopped via a load cell, and this load cell can then measure the torque that the rider is applying. Obviously, there's a little bit more going on because due to the platform motion, we have part of the torque acting just due to the motion of the platform and not due to the motion of the rider. But we have built some models to compensate for that. And with this, we are able to really measure what the rider is doing on top of the bike. And then with that, you can ride free-handedly. Or you could also use this torque measurement to put your feet down and balance the motorcycle in between yourself. Obviously, this comes with a few challenges. So we see that we have to compensate the platform motion, as I talked before. Also, we have to interpret the rider motion with respect to the motion cueing algorithm. So depending on the motion that we apply to the platform, this will change. And NVH is a big topic. As soon as we induce vibrations to the platform, this will disturb the sensor signals. Okay. The second point we want to talk about is the motion cueing algorithm and the steering control. Our requirement was that the proprioceptive and haptic feedback is rather crucial for the rider to control the motorcycle. And the vehicle is susceptible to lateral dynamic inputs from the rider. And this motion that the platform or the motorcycle does also then has implications on the steering behavior and the stability perception of the motorcycle. So therefore, it was clear for us at the beginning, we want an active system. We do not want a static simulator, we want a dynamic one. We want to use motion cueing algorithm, and we want to use active steering feedback. There are some difficulties with that. Obviously, when you're riding a real motorcycle at 45-degree of roll angle, you are pushed into the saddle because there's a lot of lateral acceleration going on. We don't have that on a simulator. Therefore, when we tilt the motion platform 45-degree, we would fall down rather than being pushed into the saddle. So obviously, there have to be some translations being done there to make it feasible. One would argue that in that case, it would be just perfectly fine and reasonable to keep the motorcycle simulator upright because the resultant force is vertically with respect to my body. But we have done some studies, and we found out that actually the study participants preferred a motion cueing being active. They preferred to be presented with a roll angle. And yeah, we have the data for that. And since we have done that study in 2015, we followed that path, and we are very happy with that. Yeah, the whole motion cueing, as I said, is also very depending on the steering behavior. There are different control concepts like impedance control and admittance control that one might know from robotics. And unfortunately, these two control theories, they go like a separate path. But in the motorcycle domain, we basically need both of them, as the one algorithm would perform better at low speeds when we have large steering angles, while the other control algorithm would especially benefit us at high velocities when we have a very stiff steering. And what we have found out then is if we start tweaking all these control algorithms and playing with the gains of that, that, for example, just a small change of the platform roll angle gain will have a huge impact on what you feel in the steering. So suddenly, when you have more roll gain, you will feel a weaker, softer steering. So there are a lot of cross-correlations in that regard.
So another challenge we had when designing that simulator is that in the passenger car domain, typically a lot of the environment is covered by the bodyworks of the car itself. But for the motorcycle rider, he or she, of course, has the possibility to look down on the road, for instance, and the peripheral vision of how the road is kind of going underneath your motorcycle is an important cue for speed perception. So we needed to come up with a solution so that our environment is providing these cues to the rider itself, and therefore we added a floor projection screen, for instance, so that the rider gets those cues necessary to judge the speed appropriately. Another solution is, of course, working with VR glasses, which we did, but both of it comes with certain other challenges. On the one hand side, of course, you have a vertical screen and a horizontal screen, so there's a certain bias in how you present the virtual environment with a floor projection screen. And on the other hand side, with our customers, we are typically interested in how the riders interact with the HMI, for instance, with different controls on the handlebar. And if you're working with the VR glasses, you're missing the natural side of your hands. That is why this is not I would say, the one and only solution, and we tailor it to the research question that we have, which one to use. Another big topic was that in the beginning, the riders were somehow lacking the proper feeling of speed and also acceleration or deceleration. When is braking feeling like a hard braking and when it's just a soft braking? So we said, okay, there's an important kind of proprioceptive cue is missing. In reality, you have the wind forces towards the torso of the rider, for instance, so you feel the muscles in your stomach or in your neck that you need when going with 120 kilometers per hour, for instance. And to compensate that, we built this rope towing mechanism, which substitutes those drag and inertial forces to the torso. And we ran a study and comparing whether this really creates a benefit in terms of speed perception. And it clearly does. So at the moment, we are using this for the longitudinal cues. For acceleration, you're being pulled to the back, and for deceleration towards the handlebar. And this is working quite well, and the challenge was a bit, how do you apply this force towards the torso so that it does not feel like you were wearing a backpack? And our solution was working with this motorcycle airbag jacket so that you have a surface load on the whole torso, which feels more natural, let's say. Of course, mechanical issues such as backlash and so on remain, but those have been solved in other topics as well. And we had an interesting project together with VI-grade and the Technical University of Darmstadt, where we also thought about adding another direction to this, let's say, control or rider input. So we could also pull the rider to the side and keep him or her in a certain position. And this can even be exceeded with more directions, but we might hear more about this later on from Diego.
Yeah. All the technical setup, software, etc., was done very easily, thanks also to the VI-grade system. So we were able to integrate BikeRealTime within a framework of a Simulink model, which is then compiled into C code that is then being used in our own simulation environment. We can talk a lot about all these design topics, but the most important thing maybe for here is also with the VI-grade toolchain, it is able for us to test different customer models, even if those files are obfuscated. So we can just receive any model, any dynamics model from any customer, and without any issues with IP, for example, and bring it onto our simulator. Obviously, this brings one challenge. How do these model adjustments cope with mock-up that is basically constant? We are not changing ergonomics, etc., at least for now. Okay, so these have been a few points where we have concentrated during the development in the recent years. And that brings us to the conclusion. We have done in the recent years many studies, successful human factors related studies, talking about distraction assessment, rider assistance, etc. This is the main part that we are doing with our Human Factors Institute, but also, obviously, we want to concentrate on the dynamic aspects. We have done emergency brakes with motorcycles. We have done a naive rider study where pure motorcyclists that had no experience with any kind of simulator were able to ride our simulator just by knowing how to ride a motorcycle. And we also investigated effects of varied vehicle setups, as we have shown before with these different motorcycle types, that study that we did, for example, with KTM. In the future, we want to concentrate a little bit more on some further developments, which is, the one step would be to go a little bit further towards the simplicity of the setup. We see that our Desmori simulator can be a little bit overwhelming. It's sometimes easier for a customer to use a simple-to-use, very stripped-down simulator, but obviously we also want to improve on the technology. And you see the image before, like multi-directional vestibular feedback, multi-directional rider input is definitely something that we have a look into in the future. And yeah, with that, we conclude our presentation. Thank you.
Thank you.